In this video, I'm going to show you how to use the program for response plots for a given predictor. I'll go down to the button down here where it's located. I'll click on it. When I do, a set of instructions appears in the description box that tells you how to use it, but we won't cover that. And then we'll be inputting data into the input values box here. Because this uses raw data, I have to go get the data first, so I'm going to click on Choose File. The data are in the folder CRET, and I'll scroll down to it, and it's going to be the file vaccine r.txt. This shows you a list of the variables that are in the data file, and this list is very important because when I enter information in the input values box, I'm going to have to refer to some of these variables. R is case sensitive, so I need to make sure I get both the spelling and the case correct. I'm going to type in up here the folder and the file name where the data are located so we know exactly where to go find it. And now we're ready for input. Okay, the program, it generates a plot for a target predictor in a logistic, probit, or OLS regression. It helps you appreciate the effect size for a predictor, holding the other predictors in the equation constant. For logistic and probit regression, it generates plots in units of probabilities. For OLS, it can help you appreciate interaction effects and polynomial nonlinear effects. I'll build on increasingly complex examples, but each focus on the same topic area, predicting whether people obtain a vaccination for a disease, scored 1 is yes, 0 is no, based on their perceived susceptibility to the disease and their perceived severity of the disease should they contract it. The latter two concepts are measured on a -3 to +3 continuous metric, where numbers less than 0 indicate lowered perceived severity and susceptibility, 0 is a neutral point, and scores greater than 0 indicate higher perceived severity and susceptibility. Okay, the first thing I have to do is to indicate the type of analysis that I'm going to use. In the description box, it tells me my alternatives, and if I want a quick reminder, I click on the toggle here switch, and I'll work with logistic regression to show you the program initially. So I'll leave this at 1. Down here, I'm going to put in the regression equation that I'm going to be working with. And in this case, the vaccine variable is called VAC-ME, is the outcome. That's the binary outcome. And then I'm going to be predicting that from P severe plus P suscept plus I'll put in as a covariate age in order to illustrate some things. The target variable that I want to analyze is going to be one of these, and I'm going to pick susceptibility as my target. Then I'll explain these other boxes to you as the models get more and more complex that we're going to work with. However, here I'll just click Register Input in order to do this binary regression logit model with some extra detail presented for the susceptibility predictor. So I'll click Register Input. That will generate the syntax we need to run in the R syntax box here. I'll copy that to the clipboard. I'll start R. Up here I'll hit Control V to paste the syntax, and when I paste it, it'll execute. And when it's done, the output is in blue and the input is in red, so we want to focus on the blue. Okay, let's look at the output first and then we'll take a look at the graph. The sample size is 500, and then what's presented here is just a straightforward logistic regression analysis. These are the coefficients for the different predictors and the standard errors and the z-values, and you can see that P severe and P suscept are statistically significant, but that age is not. And I'm not going to go over this in too much detail because this is not about logistic regression. It's about the plotting of probabilities for a given predictor. In addition to the traditional output from the logistic regression, it gives you the confidence intervals for the coefficients. It gives you the coefficients as expressed in odds ratios, and it gives you the confidence interval for the coefficients expressed as odds ratios. So all that information is pretty standard in logit modeling. Okay, the program generates a plot, which is over here, which is of interest. Here's the susceptibility scores ranging from -3 to +3. And then it plots for each of the scores across the -3 to +3 metrics, the probability that a person obtains the vaccination. So instead of working with odds, this is showing you how the probability varies as you move across the target predictor. And logistic regression is known for probabilities to have an S-shaped curve, and this is part of that S shape. It's mainly linear. It's primarily the linear part of that S shape, and it's starting to bend up here, and it's starting to flatten out down here. But this is the range of probabilities that we see. Down here, these lines, this is called a rug for a plot. Each score gets a line where there's a lot of lines that overlap or appear together. That means there's a lot of cases there. And when you see just a few lines, that means there's very few cases there. And most of the action where we feel most confident is making inferences about the center part of the rug where the dark areas really are. So most of the scores are really kind of between here and here, which is even more linear. If I wanted to, I could probably easily apply a modified linear probability model to this. The gray area in the plot is a 95% confidence band, and so that gives you a feel for the confidence interval. And you can see that as you move across the susceptibility predictor, the probabilities are ranging from down around 0.15 to up around 0.8. And you can see the slope of the curve is fairly large. Now this is the estimated effect of perceived susceptibility holding constant the other predictors in the equation. So that's also an important concept to keep in mind, that this is a partial curve. In addition to the plot, the program gives you detailed results, and let me go through those very quickly with you. First of all, the target predictor varies, and here it's starting at a low score of -2.99, and it continues to go up, and it'll go up down through these scores. And then it holds constant the other predictors at a specific value. And specifically, it holds the other predictors constant at their median values. So P severe is held constant at a value of -0.06, and age is held constant at a value of 45. This is the predicted probability for this profile, that is, people who have a -0.06 on P severe, -0.299 on perceived susceptibility, and they're 45 years old. The proportion of them, or the predicted probability of them, getting a vaccine is 0.077, and then these are the confidence intervals about that. It gives you that for about 100 different profiles, and these are the points that are used to generate the plot over here. So this is just giving you information about how, as perceived susceptibility goes up, if you want to look at the actual predicted probability or proportion of people who get vaccinated with that score on perceived susceptibility holding constant, P severe and age, this gives you that information. All right, let's close this and do another example. Let's do a case where the target variable is a qualitative variable or a nominal variable. So I'm going to add a variable of whether or not the person is Latino, which is in the variable Latino from over here. And I'm going to make that my target variable. And in the case where you have a nominal variable, you have to list it in the equation here first. And then you have to tell the program how many nominal variables you have. In this case, I have one. And the reason is that the program's going to convert this to a factor in R. It's going to automatically generate the dummy codes for you and then run it in the equation. Now this is a binary nominal variable, 1 if you're Latino, 0 if you're not. And so I'm going to analyze that using Latino as my target variable, and we'll see what the output looks like for that. I hit register input to generate the syntax. I copy that to the clipboard. I open up R. I'm going to hit Control V to paste it, And here's the plot over here. It's a little bit different. And here are the results here. Again, I get the sample size, the traditional logistic run. In this case, the dummy variable for Latino was non-significant. There's very little difference in the log odds between those. You get the confidence intervals for the coefficients, the odds ratios, and the confidence intervals for the odds ratios. Now, if we look at the plot, what I can basically see in the plot is the blue line is the proportion of non-Latinos who obtained a vaccination. You can see that's just above the 0.50, and this is a confidence band here, the gray area, and then this is the predicted probability or proportion of Latinos who got vaccinated, and there's very little difference between those. And when we come over here and look at the detailed results, again, here's the non-Latino and Latino. Perceived severity is held constant at its median value. Perceived susceptibility is held constant at its median value. Age is held constant at its median value. And here are the two predicted probabilities or proportions and the confidence intervals about those. Okay, so that's how you can look at a probability for a categorical variable. Now, if I close this and come back up to show you another angle with this, let's suppose I leave all these variables in as predictors, but now I change the target variable to perceived susceptibility again. I'm going to register that. Here's the syntax. I copy that to the clipboard. I'm going to open R, hit Control V to paste. And now I get the perceived susceptibility effect on vaccination in probability units, like in our first run. But now it's holding constant age, perceived severity, and the Latino binary variable. And if we go to the detailed results, you can see that it's holding this constant at severity at its median. It's varying susceptibility. It's holding age constant at its median. And in the case of a categorical variable, it will hold it constant at the category that occurs more frequently. Okay, so that would be non-Latinos in this case. And then these are the predicted probabilities and the confidence intervals about those. Okay, let's go back and I'll show you another feature of the program. But let's go ahead and remove the nominal variable for purposes of showing you something a little more simpler. And recall that when I did this analysis first, it looked at the effect of susceptibility holding the probability of severity constant at minus 0.06 and age constant at 45. And what I can do if I want to is to hold these constant at different values than that. The program chose the median value, but I might want to look at the effect of susceptibility on vaccination, holding those constant at different values. And I can do that with the conditional override box where I override the defaults. And in this case, I might say I want to look at the effect of susceptibility on vaccination when severity is equal to 0 and when age is equal to 30. So I want to see what happens for 30-year-olds. So you can put in any conditional overrides you want in the conditional override box here. I'll register the input. I'll copy the generated syntax to the clipboard. I'll open up R. I hit Control V to paste it. And the curve pretty much looks the same. But if I go up and I look at the detailed results, I can see that perceived severity is now held constant at 0 and age is held constant at 30. And these values do change a little bit because that's the nature of logistic regression. And this tells me what the predicted probabilities are at each profile and the confidence intervals around those. So you do have the possibility to override and to explore different conditional values in the predictor profile. Okay, let's do a run where we put in an interaction effect. I'll first show you the case where I have a qualitative moderator, and then I'll show you the case of a continuous moderator. So I'm going to erase this, and I'm going to put Latino back into the equation down here. So I have a qualitative variable in here. I'll indicate I have one qualitative variable. Down here I have the main effect terms, and so I also have to enter in the product term. And I do that by typing in Latino times P severe. Now, if you happen to have the product term in your data set, turns out I don't in mine, but you would not enter that already derived product term into the equation here. You have to actually put in the multiplicative product term here so that the program knows that this is an interaction term with these other component part variables already included. And actually what I want to do is I want to put in P suscept here because I'm looking at the interaction between susceptibility and Latino. Here, my target variable is within that interaction term, susceptibility, so I have to indicate which variable is the moderator variable, and in this case it's Latino. So I want to see if the effect of perceived susceptibility on vaccination differs as a function of whether or not someone's Latino, and that's the interaction effect here. Now, interaction effects in logistic regression are kind of controversial. Some people work with odds ratios when analyzing interaction effects, but there's quite a bit of support for working at the level of probabilities rather than the level of odds and odds ratios when studying interactions in logistic regression. And that's because the odds ratios can be quite misleading, as I discuss in my book. The advantage of this program is it's going to do an analysis of the interaction effect, but it's going to do so using response probabilities. Okay, I'm going to click on register input to generate the syntax. I'll copy that to the clipboard. I'll open up R. I'll hit Control V to paste it, and up comes the results. So we go up and again we get the traditional output for the logistic regression. Here's the interaction term here, the coefficient estimate for it, standard error, the z-value, and the p-value for it, and it's not statistically significant. The confidence intervals, and then everything translated into odds ratios and confidence intervals for them. Again, I'm not focusing on the logistic part of this because I cover that in my book. You can get the ins and outs of that there. And my main goal is to show you how to look at predicted probabilities and how they vary as a function of a predictor holding the other predictors constant. If I look at the plot over here, this is the plot for people who have a score of 0 on Latino, and this is for people who have a score of 1. And if we look at the plots, we can see the curves are very similar to one another. These are the probabilities of getting a vaccination as the susceptibility increases. It's not surprising that the interaction term was not significant because these effects, they look fairly comparable. Now, it is possible, as I discuss in my book, in logistic equations, to get a non-significant product term, but for there to be very clear-cut interactions going on at the level of probabilities. And that's why we generally want to look at probabilities as well when we evaluate interactions. If I come over to the detailed results, here I'm holding Latino constant at 0. Severity is held constant at minus 0.06. Susceptibility varies. Age is held constant at its median. Here's the predicted probability or the proportion of people with this profile who get a vaccination, and then the 95% confidence intervals over here. And you can see in the detailed results, I first of all get the results when Latino is 0, and then as we scan down, then I get the comparable results when Latino is equal to 1. So it's giving me information for both groups that correspond to the plots. Again, I find it useful to look at this more detailed information. Okay, if I close this, I can also do this same run, but again, I can override where I hold the variables constant. So I can do this analysis where I set P severe equal to 0 and age is equal to 30. I can re-register that. I copy this to the clipboard. I start R. I hit Control V. Plots look pretty much the same in this case. And if I go back up to the detailed results, I can see perceived severity has been held constant at 0 and age has been held constant at 30. So if I want to say for non-Latinos who perceive severity as 0 and they tend to not see themselves as susceptible and they're 30 years old, what proportion of them will get the vaccination? It'll be about 12%. And then these are the confidence intervals about that. And I can pull off example cases from this as I discuss the results. Okay, let's close this and look at a continuous interaction. I'm going to change the outcome variable because I've created the data in this case so that the interaction will show up, so that we will get an interaction. So the outcome variable is still whether or not someone gets a vaccination, but I've made it such that we are going to get an interaction. And my predictor variables are going to be P severe, P suscept, age, and then I'm going to put in the interaction term. And the interaction term is going to be P severe times P suscept. That is, I'm going to look at the interaction between these two continuous variables, predicting whether or not people get vaccinations. I no longer have a nominal variable in the equation. I'm not going to do the conditional overrides. My target variable is going to be perceived susceptibility, and I'm going to see how the effect of that variable varies as a function of perceived severity. My hypothesis would be that when perceived severity is pretty low, perceived susceptibility is not going to have much of an impact, because if you don't see it as a serious disease, you don't really care if you get it. So the effect of increased susceptibility to it is not going to have that much of an impact on whether or not you get a vaccine. But on the other hand, if you see this as a very severe disease, then the impact of susceptibility is going to be stronger. So I expect an interaction between these two. Okay, now because this is a continuous variable, what the program's going to do is it's going to look at the relationship between susceptibility and vaccinations at different levels of severity. And here I can tell it to look at 3 different levels of severity, or I could tell it to look at 5 different levels of severity and to plot the effect of susceptibility on vaccinations as you break this into low, medium, and high values and break it into 5 different categories. Now I'm going to break it into 3 categories, and what will happen is the program will use its default to choose a low score on severity to look at the relationship between susceptibility and whether or not you get a vaccination, a moderate score, and then a high score. So if you just put in a number here, that's the number of breaks that you want, and the program will automatically define those breaks and show you the results accordingly. I'll show you how to override that and to actually specify where the breakpoints are in just a minute. But let's take a look at the output here. I'll hit register input. That generates the R syntax. I'll copy that to the clipboard. I'll open up R. I hit Control V. And I get the results from the logistic regression up here. And if we look at the interaction term, you can see that's highly significant. And I get the confidence intervals for it and the odds ratios for it. and the confidence interval for the odds ratios. Again, I go into my book how to interpret all these things. I'm not going to do that here. And then here are the three plots that the program generated for me. Here's when severity, remember, it ranges from -3 to +3. And here's when severity is equal to -1.4. So this is the low score. Here's where severity is equal to right around 0. So this is a moderate score. And here's where it's equal to 1.2, which is a relatively high score. Here are the rugs underlying these. And you can see that when perceived severity is low, that as perceived susceptibility goes up, the vaccination rate, measured in probabilities or proportions, doesn't change very much. This is relatively flat. When severity is near 0 or in a middle score, you can see as susceptibility goes up, the probability of getting a vaccine goes up. And again, this is holding constant the other variables, age. And then here at a high score, you can see this slope is much steeper, and then it accelerates much faster. So you can see right here that the effect of susceptibility on vaccination rate does vary as a function of whether or not severity tends to be low, moderate, or high. And then you get the detailed results over here. Here it's holding severity constant at -1.3589, which is rounded -1.4. There's susceptibility varying. Age is held constant at 45, and these are the proportions and confidence intervals here. And it gives you this detailed results for, first of all, the case when severity is low, and there it is when severity is medium, and then when severity is high. So you get the detailed results throughout. I'll close this. Now, instead of letting the program choose them, I can force the program to put the breakpoints at values that I want. So instead of just telling it to do 3 breakpoints, I'll actually specify the values of the breakpoints I want. So I might put in -1, 0, and 1. And then it's going to do 3 breaks. One of them will be where perceived severity is at -1, and then at 0, and then at 1. So I hit register input, copy that to the clipboard, I start R, I hit Control V. Plots pretty much look the same, but when I look at the detailed results, I'll see that the variables have been held constant, perceived severity, at -1, and then later 0, and then later 1. So this is a nice program, I think, for looking at the relationship between a target predictor and an outcome using probabilities and looking at probability curves and seeing the effect of a predictor on the probability of the outcome, holding constant the other predictors in the equation. And I often use this to help give me a feel for the effects of variables on probabilities when I'm doing logistic or probit regression. All right, let's close this. And let's take an example of using OLS and looking at it with a curvilinear function to see what that looks like. So I'm going to change the analysis away from logit, and I'll put in a 3 so that I'm doing ordinary least squares. And I'm going to, in this case, predict a continuous measure of the intent to get a vaccination that's called VAC-POW, that's here. And that measure is a continuous measure. It ranges from 0 to 10, with higher scores indicating a greater intent to get a vaccination, and 5 is kind of a neutral point. So I'm now working in an OLS situation rather than a binary outcome situation because I'm predicting a continuous outcome. And I'm going to predict that from, in this case, perceived severity, perceived susceptibility, and I'm going to see if income predicts the intent to get a vaccination over and above perceived severity and perceived susceptibility. So I'm going to be looking at the effect of income on the intent to get a vaccination, holding constant perceived severity and perceived susceptibility. Now in this case, I've constructed the data so that income is curvilinearly related to the outcome because I want to illustrate that. So what I want to do is to add a quadratic term for income. Now this works just like an interaction. If you already have the product term, or quadratic term in this case, in your data set, you don't want to enter it in because the program has to know that there's this dependency between income and income squared. So you have to put in, using R notation, the polynomial term. The notation that R uses for a polynomial, which I give in the instructions, is you use the letter I, and then in parentheses you put the variable you're zeroing in on, and then you put a little hat sign and you square it. So that's like saying income plus income raised to the second power, or this is the quadratic term here. When R sees the same variable in both of these and you're using this notation, it knows that there's a dependency between these two terms, and it will take that into account. Okay, I'm going to get rid of the moderator variable because there's no interaction. The target variable is going to be income. And there's no breaks because there's no interaction effect here. And income is measured in units of thousands of dollars. Okay, so a score of 10 means the person's annual income is $10,000. 20 means that it's $20,000, and so on. Okay, I'll hit register input to register the syntax. I'll copy that to the clipboard. I start R. I hit Control V. Here's the output. Here's the outcome, is the intent to get a vaccination. Here are the different coefficients. And here's the non-squared income variable, which is statistically significant, and then the quadratic term, which is statistically significant. Again, I'm not going to go through the interpretation of these because I do that in my book, and I'm going to assume that you know that and are comfortable with those. You get the confidence intervals for them, and then you're going to get the detailed results, which I'll go over with you in a little bit. Okay, over here on the plot, here's the income variable. It ranges from $10,000 to $70,000 for this particular sample. And here's income as it goes up from 10 to 70. And then here's the mean of the vaccination intent on its 0 to 10 scale as a function of each one of those points on the income scale. And again, we get the rug down here. And you can see that there is, in fact, a curvilinear relationship between income and the intent to get a vaccination. When income is low, the intent is low, and it increases as income goes up to a point. And then when you reach right around $50,000, $55,000, increases in income lead to decreases in the intent to get the vaccination. And then I'd have to put a substantive interpretation on that. Here I get in the detailed results, I get the value that the perceived severity was held constant at, the value that perceived susceptibility was held constant at. Here's the variation in income. Here's the predicted mean for those. And then here's the confidence intervals around that predicted mean that was used to generate the confidence band. So the program also is very useful to help us look at curvilinear relationships within OLS. You can also plot interaction effects in OLS, and I find the program to be pretty useful for getting an appreciation for effect sizes of predictors and interactions and nonlinearity. The name of the program is VisReg, V-I-S-R-E-G. There's some really good tutorials for it out there on Google. So I recommend that you go and dig up those tutorials so that you can exploit it in more detail than what I've shown you here. Okay, that's it. Thanks a lot.